In this video, I'm going to take a look at the KZN Physical Sciences Grade 10 November 2025 Paper 1. Question 1.1, pulse P moving to the right with an amplitude of x meters overlaps pulse R moving to the left to form a trough with an amplitude of 2,25 x meters. Which of the following combinations will be correct when the pulses meet? Because P is above the medium and R is below the medium, the type of interference that we're going to get is going to be destructive interference. So A can be eliminated and C can also be eliminated. Now I'm going to set an equation to work out the amplitude of pulse R. Since a trough forms, I'm going to use R as the larger value. I'll say that R minus P, because this is destructive interference, so you subtract, is equal to the resultant, which is 2,25x. Now they tell us that P has an amplitude of x, so R minus x equals 2,25x. Then you take the x over, R is equal to 3,25x. The answer then is going to be D. Question 1.2, which of the following indicates the region of low pressure in a longitudinal wave? A longitudinal wave looks something like this. This region is a region of high pressure and it is called a compression. This is a region of low pressure and it is called a rarefaction. The answer is C. Question 1.3, a 12-volt battery is connected to 3 resistors as shown in the circuit diagram below. Which of the following combinations of voltmeter readings will be correct? Now, we have a parallel connection here. So this is in parallel with this. Let's use this color. Now, the resistance of R2 and R3 are both 2Y. So the effective resistance in parallel, so 1 over R parallel is equal to 1 over 2Y plus 1 over 2Y. So 1 over R parallel is equal to 2 over 2Y. We can cancel the 2's. That means that 1 over R parallel is equal to 1 over Y. That means R parallel is equal to Y. So what that means is effectively we have a circuit that can be simplified to this. We have a resistor here of Y, and then the parallel has a resistance of Y as well. So 12 volts here. Now, resistors in series are potential dividers. Now, since these two resistors are essentially the same, well, they are the same, the potential difference or the voltage must be the same. So 12 divided equally among 2 must be 6 and 6. So the answer we're looking for is going to be 666B. Question 1.4. Which one of the following statements are true? An object experiences negative acceleration when it is moving in the... So negative acceleration essentially means that the object is slowing down. So its velocity is decreasing. So moving in negative direction at constant velocity, that's out. Positive direction, experiencing a constant decrease in speed. C, negative direction, experiencing a constant decrease in speed. Or D, positive direction, experiencing a constant increase in speed. I think it's clear here that D and C are going to be out. The answer is going to be B. Because if you imagine a car that is moving to the right, that is the positive direction. It is slowing down, which means that the acceleration is in the opposite direction. So slowing down. Question 1.5. The mechanical energy of an object dropped from the top of a building of height h meters is E. Which one of the following is the mechanical energy of the object when it is a quarter h meters above the ground? The answer is going to be E. because the total mechanical energy in an isolated system is conserved. Mechanical energy throughout the whole system is going to be the same. Let's move on. Question 2. 2.1. During an earthquake, seismic waves travel through the Earth's crust. In a type of seismic wave called P waves, the particles in the medium move back and forth in the same direction that the wave travels. A seismic station located 300 kilometers from the epicenter of an earthquake detects the first wave 45 seconds after the start of the earthquake. The measured wavelength of the seismic wave is 3,600 meters. Question 2.1.1. Are seismic waves described as transverse or longitudinal waves? So they are going to be called longitudinal waves. That's because they tell us that they move in the same direction as the wave, so parallel. Question 2.1.2. Calculate the speed of the wave. So we can calculate this using the formula speed is equal to distance over time. So the station is 300 kilometers away, so that's 300,000 meters divided by the time that it takes for the wave to travel, which was 45 seconds, and that's equal to 6,666,67 meters per second. Question 2.1.2b. Calculate the frequency of the wave. We can use the formula v is equal to f times lambda. We know the speed, so 6,666,67 is equal to f multiplied by the lambda. They tell us the lambda is 3,600, so 3,600. We can solve for f. F is equal to 1,85 hertz. Question 2.1.3. Determine the number of waves that pass the seismic station in the first minute of the earthquake. So we know the frequency, so let's calculate the period. So period is equal to 1 over frequency. We can substitute, so 1 over 1,85, and that's equal to 0,54 seconds. So this is 0,54 seconds for one wave to pass. Now, the station is not actually recording the wave for a full minute, because remember they tell us that it took 45 seconds for the wave to reach the station. So from 0 to 45, there's no wave. So the station is only recording for 15 seconds. So now we can do cross multiplication. We can say 0,54 seconds is one wave. That means in 15 seconds, there will be x waves. So we can cross multiply here. We will get 1 times 15 is 15, and that's equal to 0,54x. That means x is equal to 15 divided by 0,54, which is equal to 27,78 waves that's going to pass in that 1 minute. Moving on to question 2.2. An earthquake produces a loud sound of frequency 490 Hz that travels through the air. A town lies 6,500 meters east of the earthquake's epicenter, and the sound wave from the earthquake reaches the town in 19 seconds. The speed of sound in air does not change between the epicenter of the earthquake and the town. Question 2.2.1 we can leave out. Question 2.2.2, determine the wavelength of the sound wave. So this is worth 5 marks. So first we can calculate the speed of the wave. So speed is equal to distance divided by time. The distance that it traveled was 6,500 divided by the time that it took was 19 seconds. And that's equal to 342,11 meters per second. Now that we know the speed, we can use the formula v equals f times lambda to calculate the wavelength. So 342,11 is equal to the frequency, which they told us was 490, multiplied by lambda. That means lambda is equal to 0,70 meters. Moving on to question 3. Sunscreens contain ingredients that absorb UV radiation before it damages skin cells. A photon of UV radiation, UVB, has a maximum frequency of 1,2 times 10 to the 15 Hz. Photon energies of at least 4,5 times 10 to the negative 19 joules results in damage to DNA. Question 3.1, use suitable calculations to show that UVB will cause damage to DNA. So I'm going to write 3.1 here. So we can use the formula E is equal to HF. So we want to calculate the energy and then compare it to the energy that causes damage. So H is 6,63 times 10 to the negative 34 multiplied by the frequency of the UVB, which is 1,2 times 10 to the power 15. And that's equal to 7,956 times 10 to the negative 19 joules. Now, this value right here is greater than 4,5 times 10 to the negative 19, because that was our minimum value, because they tell us at least that amount. So therefore, it will cause damage. The energy is greater, and so it will cause damage. Moving on to question 3.2. A sunscreen claims to absorb UV radiation with wavelengths as short as 300 nanometers. Determine if the sunscreen will provide protection against UVB. So what we'll do here is we're going to calculate the wavelength and then compare it. So I'm going to use the formula. So for 3.2, now since this is part of the EM spectrum, all the waves are going to move at a constant speed. We call that C. So the formula is C is equal to F times lambda. So 3 times 10 to the power 8, that is the speed of light, is equal to the frequency, so 1,2 times 10 to the power 15, multiplied by lambda. So lambda is equal to 250 times 10 to the minus 9 meters. Now 250 times 10 to the minus 9 is less than 300 times 10 to the minus 9. So because it is less than, because they tell us here that the sunscreen claims to absorb UV radiation as short as 300. So it's 300 and above that it can actually absorb. So because this is less than 300, we can say that it's not going to protect against UVB. So will not protect against UVB. Moving on to question number 4. Two identical conducting spheres X and Y are placed on insulating stands. The charge on both spheres is unknown. The spheres are allowed to touch, resulting in electrons moving from sphere X to Y and are then separated. So after separation, each sphere now carries a charge of 2 times 10 to the minus 6 coulombs. The charge on each sphere changed by 4 times 10 to the minus 6. Question 4.1, write on the principle, we can leave that out. Question 4.2, calculate the number of electrons that were transferred in this process. So I can use the formula N equals delta Q divided by QE. Now the change in the charge has been given to us. So 4 times 10 to the power minus 6 divided by the charge of an electron, 1,6 times 10 to the power minus 19. And that's equal to 2,5 times 10 to the power 13 electrons that have been transferred. Moving on to question 4.3. Determine the initial charge on sphere Y. So because they tell us that electrons moved from sphere X to sphere Y, it means that X has become more positive. So it has become more positive. It lost electrons. Therefore, Y has become more negative. So we can actually work with the change in the charges. So the change in the charge for X is going to be positive because it lost electrons. When you lose electrons, you become more positive, and so the charge or the change in the charge will be more positive. So the change in charge for X is going to equal 4 times 10 to the minus 6. However, the change in the charge for Y is going to be negative because it gained electrons, it gained charges. So minus 4 times 10 to the minus 6. So we can use the formula here. Delta Q is equal to Q final minus Q initial. The change in charge for Y is minus 4 times 10 to the minus 6. That's equal to, the final charge on each sphere is given to us as 2 times 10 to the power minus 6. So 2 times 10 to the minus 6 minus the initial charge. Now we can solve. The initial charge is going to equal 6 times 10 to the minus 6 coulombs. And then for the next one, we can repeat the same process. The delta Q for X is going to equal the Q final minus the Q initial. So because X lost electrons, it lost charges, its change in charge will be positive. So 4 times 10 to the power minus 6 is equal to, the final is 2 times 10 to the power minus 6 minus the initial. The initial is then going to be minus 2 times 10 to the power minus 6 coulombs. Moving on to question 5, electricity. A battery with an EMF of 18 volts is connected to 4 resistors as shown in the circuit diagram below. The connecting wires and the battery have negligible resistance. 0.5 amperes of current passes through the 6 ohm resistor. Question 5.1 is a definition, we can leave that out. Question 5.2, determine the reading on ammeter A1. Let's use the fact that because these are in parallel, the voltage across both of them are going to be the same. So I can say here that V is going to equal IR. So the current is 0.5 multiplied by the resistance is 6. That's equal to 3 volts. Now the voltage here is also going to be 3 volts. So V is equal to I times R. 3 is equal to I times 12. That means I is equal to 0.25 amperes. So the reading on A1 is going to be 0.25 amperes. You could, of course, use ratios and say that because the 6 ohm is half of the 12 ohm resistor, the current that's going through the 6 ohm resistor will be double, because remember that current takes the path of least resistance. So to work out A1, all you needed to do was say that half of 0.5, and that's going to equal 0.25 amperes. Either one works. Moving on, question 5.2.2, determine the resistance of resistor X. Now, in order to figure out what the resistance of resistor X is going to be, we should figure out what the voltage for X is going to be. So we've already worked out that the voltage here is 3 volts. That means resistor X needs to use up. So remember that the battery is giving 18 and the whole thing is in parallel. So this branch here would use 18 and this branch here will use 18. But 3 is already used up for this small parallel branch inside. That means this must be 15 volts because 15 and 3 gives you 18. Now we just need to figure out what the current is and then we can work out the resistance. We know the current going through here is 0.5 and we also know the current going through here is 0.25. So that means the current in this branch here will be the sum of 0.5 and 0.25. So the current, if we had to connect an ammeter here, the current will be 0.5 plus 0.25, which is equal to 0.75 amperes. Now that we know the voltage and we know the current, we can work out the resistance. I'm going to say that R is equal to V over I. So the voltage we said was 15, the current was 0.75, and that's going to equal 20 ohms. Question 5.2.3, calculate the energy transferred in the 6 ohm resistor in 3 minutes. So the 6 ohm resistor, this one right here. We can use the formula W equals V times I times T. There are other formulas that you could use. I'm using this because these are the values that we calculated. We know the voltage was 3 multiplied by the current was 0.5 and the time is 3 minutes and then converted to seconds, so 3 times 60, and that's equal to 270 joules of energy that's been transferred. Moving on now to question number 6. A rugby player catches the ball at point A, 10 meters east of the halfway line on a standard 100-meter pitch. The halfway line is on the 50-meter mark. The player then performs the following sequence of movements along a straight line. So run 30 meters westward toward the opponent's try line in 6 seconds. Gets tackled and is pushed 15 meters eastward in 3 seconds. So this way 30 meters. Then this way 15 meters. And then recovers and sprints 25 meters westward, so 25 meters that way in 5 seconds before passing the ball. Question 6.1.1 is a definition. Let's leave that out. Question 6.1.2, write down the position of the player relative to the halfway line after the first 6 seconds. So 6 seconds here. He goes 30 meters west. So if he's here and he goes 30 meters this way, then how far away is he from the halfway line? He is 20 meters. He is going to be 20 meters west of the halfway line. So 20 meters west. Question 6.1.3, determine the average velocity of the player for the entire motion. So in order to calculate the velocity, remember that velocity is equal to the displacement divided by the time. So let's figure out his displacement. He travels 30 meters this way. He travels 30 meters, 15 meters that way, and then 25 meters this way. So I'm going to say that 30 minus 15 plus 20 divided by, and the time that it took for him to do all of this is 6 plus 3 plus 5, which is 14. So divided by 14, and that's equal to 2,86 meters per second west. Because his overall movement is to the west. He traveled more to the west than he did to the east. So his average velocity will have a direction of west. Question 6.1.4, is the average speed for the entire motion greater than, less than, or equal to the average velocity? Explain. So in order to answer this question, we need to know how speed is calculated. So velocity is calculated by displacement divided by time. Speed is calculated by distance divided by time. Now, the time for both is the same. So time for both are equal. That means that the velocity is going to be directly proportional to the displacement, and the speed is going to be directly proportional to the distance. Now, when we calculated the displacement, it's clear here that we were subtracting values, because remember, velocity, displacement is a vector, and so direction is needed. If it goes in the opposite direction, we need to subtract. Whereas speed and distance are scalars. There's no direction needed, so there's no subtraction at all. So distance is going to have a higher value because there's no subtraction. And because the distance is going to be greater, the speed is going to be greater. And that's our answer. Question 6.2. In a different play, the rugby player starting from rest runs toward the opponent's try line due west of his initial position. So moving westerly. The player moves along a straight line. His motion is shown in the velocity time graph not drawn to scale below. Question 6.2.1. Determine the distance covered by the player for the first 13 seconds. So if you have a velocity time graph and you want to figure out the distance traveled or displacement, you need to work at the area. So the area of this shape, this is a trapezium. So you can either break it up into two triangles and a rectangle and work at the areas and then add it up, or you can use the formula to calculate the area of a trapezium. So the area of a trapezium is equal to half the sum of the parallel sides. So this is 13 plus this is from 4 to 10, so that's a length of 6, multiplied by the height. The height here is 8. And so that's equal to 76 meters. Remember, they asked for distance, so we do not need to give a direction. Question 6.2.2. The player is tackled at 13 seconds and is pushed eastward at a constant acceleration of minus 0.5 meters per second squared for 4 seconds. So this region here. Using the graph only, no equations of motion, determine the displacement of the player over the entire 17 seconds. So they've given us the acceleration. And when you have a velocity time graph, acceleration is the gradient. So the gradient of this line is equal to minus 0.5. Now that we know that, we can work out the value for z. And if we work out the value for z, we can then work out the displacement. So I'm going to write out here that the gradient is equal to the acceleration, which is equal to minus 0.5. Now, coordinates here, this coordinate is 13 and 0, and this coordinate here is 17 and z. So I'm going to use the formula. So y2 minus y1 over x2 minus x1. So this is going to be z minus 0 divided by 17 minus 13 is equal to minus 0.5. That means z is equal to minus 2. So this value right here is minus 2. Now remember that because this is below the x-axis, below the x-axis, this is moving easterly and this is moving westerly. We know that the area of this is 76 meters. So if they want the displacement, we just need to work out this area and then subtract them because they're in opposite directions. So I can then say that the area is going to equal, this is a triangle, so half base times height. So half the base is 4 multiplied by the height. I'm not going to include the negative sign here because I know that I'm going to subtract anyway. So 2, and that's equal to 4 meters, and this is easterly. So in order to calculate the displacement is going to be 76 minus 4 because this was west and this is east. So that's equal to 72 meters west. Moving on to question number 7. A train of length 180 meters is moving at constant velocity of 20 meters per second east. A car parked alongside the train takes off from rest when the front of the car is in line with the back of the train. The car also travels due east and accelerates uniformly at 4 meters per second squared to reach a maximum speed of 50 meters per second. Question 7.1, definition, we can leave that out. 7.2, calculate the time taken for the car to reach a maximum velocity of 50 meters per second east. So we know for the car that the initial velocity is 0. They tell us that. They tell us here that a car parked means the initial velocity is 0. They also tell us that the acceleration of the car is equal to 4. So they tell us here that it's 4. So we can use the formula Vf is equal to Vi plus A delta t. They tell us the Vf. So 50 is equal to 0 plus 4 delta t. That means delta t is equal to 12.5 seconds. Question 7.3. Determine the distance between the front of the train and the car when the car reaches maximum velocity. So let's calculate how far the car traveled. So the car, I'm going to use the formula delta x equals Vi delta t plus half a delta t squared. So Vi is 0, time is 12.5 plus half, the acceleration is 4, and the time is 12.5 squared. That's equal to 312.5 meters. Now for the train is moving at a constant velocity, so delta x is equal to v times delta t. The velocity of the train, they tell us, is 20, and we want to know how far it traveled in the 12.5 seconds. So that's equal to 250 meters. Now let's draw a diagram. So the train is here, and this is the back of the train. Now the car is here. So the train travels a distance of 250 meters. So from here to here. So the chain is going to be at this position. And this is 250 meters. But the chain is 180 meters in length. So the distance to this position here, the front of the chain, is 180. So that's going to be the total length. Now the car traveled 312.5 meters. So this entire length right here is going to be 250 plus 180. So 250 plus 180, and that's 430 meters. Now the car only traveled 312. So from here to about here. So the car, or the front of the car, is only going to be here. So that means that this distance here is the deficit. That's how far behind it is. So in order to work out what that length is, so let's make a note, this is 312.5. So all we need to do here is we'll say that the distance is equal to 430 minus 312.5, and that's equal to 117.5 meters. Let's take a look at question number 8. A 0.5 kilogram stone is thrown vertically downward at 12 meters per second from the top of a 50 meter high building. The bottom of a window is located 20 meters below the top of the building as shown in the diagram. Ignore air friction, which means mechanical energy. Question 8.1, calculate the mechanical energy of the stone. So at the top, EM is going to equal EP plus EK. Now EP is mgh, the mass is 0.5, so 0.5 multiplied by 9.8, and the height of the building is 50, plus half, the mass is 0.5, the velocity that it's thrown with is 12 squared. So we can calculate the EM, and the EM is going to be 100, or rather 281 joules. Question 8.2, determine the following at the bottom of the window. So here, when the stone is here, the gravitational potential energy of the stone. So here at this point, the EP is going to equal mgh. The mass is 0.5, gravity 9.8, and the height from here to here, remember it's the height above the ground, so that's going to be 30 meters. And that's going to equal 147 joules. Question 8.2.2, the speed of the stone. So how fast is the stone going when it's at that position? So here we can say that the mechanical energy is equal to the potential energy plus the kinetic energy. Mechanical energy is the same everywhere, so 281 is equal to the potential energy we worked out as 147 plus EK. That means that the EK is going to equal 134 joules. Now that we know the EK, we can calculate the speed. So we'll say that EK is equal to half mv squared. 134 is equal to half into 0.5 times v squared. That means v is equal to 23.15 meters per second. They asked for speed, so no direction is needed. And that's the whole paper. Guys, if you stuck around till the end, don't forget to leave a like on this video, share this video with more people, and I'll see you in the next one. Bye-bye.